A number of countries dream of playing an important part in what will be one of the greatest challenges of the 21st century, space development. In this program, we will talk about the Ariane rocket, how satellites are made, and the Hermes space vehicle. In 1972, a dozen European nations signed an agreement to set in motion the construction of Ariane, the first European rocket. The first Ariane rocket was developed in parts in over a dozen European countries. The parts were then sent to a launching base in New Guyana, where they were assembled like Lego. On Christmas Eve, 1979, the first Ariane rocket lifted off, almost stealing the show from the Star of Bethlehem. Europe is already well on its way to stardom. Since 1979, the European nations have their own powerful rocket, capable of transporting satellites, scientific instruments, or space probes into space. The Ariane rocket. The engineers in charge of developing Ariane followed the same basic principles as the ones that guided the making of the American and Russian rockets. Generally speaking, a space rocket has to perform three tasks. It must propel itself and gain enough speed to pull away from the Earth's gravity. It must be able to maintain its balance and follow a precise orbit around the Earth. Lastly, it must release its payload at the right time. The European engineers came up with particularly effective ways of meeting these challenges. Ariane is propelled in three stages, each with its own engines and energy reserves. This energy is provided by liquid fuel, a substance capable of combustion, even in empty space. Further, the Ariane rocket can be equipped, if need be, with boosters to increase its power. These small rockets also use liquid fuel or a combustible powder. The boosters can be put together in various configurations, giving the rocket an added thrust of varying degrees. The most powerful configuration, consisting of 4 liquid fuel boosters, will place a 4,200 kilogram payload into orbit. This is equivalent to 2 large satellites. The minute it lifts off, the Ariane rocket is completely independent from the ground. Ariane has a control module located above its 3rd stage, which is called an instrument pack. The instrument pack allows the rocket to carry out all the stages of its mission without outside intervention. The instrument pack ensures the rocket's piloting and maintains its stability and balance. It also steers it, keeping it firmly on course toward its orbit. The instrument pack is able to accomplish these tasks by using a device called an inertial reference system. The inertial reference system consists of 3 accelerometers and 3 gyroscopes. As their name suggests, accelerometers are instruments that measure the acceleration of the rocket. They are directed toward space's 3 axes. The gyroscopes analyze the rocket's changes of direction with reference to space's 3 axes. They are highly accurate and can detect a change of trajectory of 0.05 of a degree. The Ariane inertial system can also, at any time from the moment the rocket is launched, pinpoint its exact position and velocity. A powerful calculator integrates all these measurements and sends orders to the different engines. The engine's mobile nozzles can be aimed in various directions to correct the rocket's movement and position, to keep it well balanced and steady, and to guide it precisely toward its orbit. When Ariane's last stage is placed in orbit 18 minutes after the launch, the rocket executes its 3rd and final task: release its payload. The payload, which consists of one or even two satellites, can be positioned according to two main types of orbit: the low-altitude orbit and the geostationary orbit. Satellites in low orbit gravitate at an altitude of a few hundred kilometers and orbit round the planet several times per day. This orbit is primarily used for Earth observation satellites. However, the majority of satellites Ariane places into orbit are geostationary satellites. These satellites have the distinctive feature of orbiting at the same speed as the Earth, and therefore of remaining stationary over a fixed point on the Earth below. Geostationary satellites orbit at an altitude of 36,000 kilometers and on the equatorial plane. The Ariane rocket, in fact, releases the satellites into a very elongated temporary trajectory called transfer orbit. The satellites then use their own propelling systems to change the elliptic orbit into a circular one, an operation that can take several weeks. In this respect, Ariane has the advantage of being located in French Guiana, very near the equator. After achieving their transfer orbit, the satellites launched by Ariane have a shorter route to cover before reaching their final orbit along the equator. This translates into fuel economy for the satellites, and thus an increase in their useful lifespan. The first generation of Ariane rockets was designed to put an average-sized satellite into orbit. The scientists soon realized that it would be more profitable to launch two satellites simultaneously. Hence the second and third generations of Ariane rockets. Later, Ariane 2 and Ariane 3 were themselves replaced by an even more powerful launcher. To everyone's surprise, since it was thought that in time satellites would become lighter and lighter, satellites instead showed a tendency to gain weight. The 1,200 to 1,500 kilogram satellites of the 80s are obsolete. The satellites of the 90s already weigh twice that, and some over 3,500 to 4,000 kilos. A satellite is not only equipped with complex observation instruments, it also contains all the systems that ensure its flight and reliability. Telecommunications, surveying the Earth. Virtually all such areas of activity now need what satellites can offer. Great care and the leading technologies go into the design and manufacture of satellites. Satellites are generally built in two major stages. The first involves erecting the satellite's platform. The platform, which could be compared to the infrastructure of a house, performs the basic functions that enable the satellite to work flawlessly for long periods of time. The platform consists of several elements. The first is the satellite's outer structure. The outer structure, the satellite's skeleton, is generally made up of carbon fibers and an aluminum alloy in a cellular pattern. These materials give the satellite its lightness and strength. Subsystems are added to the satellite's basic structure. One of them ensures the satellite's energy supply. It contains photoelectric cells, or photocells, mounted in series on panels which are deployed by the satellite once it has reached its orbit. The cells consist of semiconductor materials, such as silicon. When these semiconductor materials receive photons, that is, small particles that make up light, they emit electrons. The free electrons then generate an electrical current. Another subsystem ensures communication between the satellite and Earth. This system consists of receiving and transmitting antennas. The former are used to pick up instructions from the ground, or remote commands, and the transmitting antennas send varied data back down to Earth, such as the satellite's position. This data is also called telemetry. Remote commands are used to control the satellite's orientation in space. This control of position, also called attitude control, is of utmost importance to the satellite. Thanks to attitude control, the direction its observation instruments, telecommunication antennas, and solar panels are pointing can be changed accurately and at will. One of the most precise means of attitude control used in satellites is the magnetic bearing reaction wheel. A magnetic bearing reaction wheel consists of a stationary part, the stator, and a mobile part, or rotor. The stator has spinning field motors that make the rotor spin very rapidly. The stator is also fitted with permanent magnets linked to electromagnetic circuits. The magnetic field created by the magnets enables the rotor to literally levitate inside the stator, nullifying all friction, wear, and vibrations. As a rule, a satellite has 3 such reaction wheels, placed according to the 3 axes of space. Owing to their rapid spinning action, the 3 wheels exert forces perpendicular to their axes. When a slight change is made to the rotor of one of these wheels, the force that wheel exerts is different from the force generated by the 2 other wheels. This slight imbalance is translated in space's weightlessness by a change in the satellite's orientation. In addition to its attitude system, the satellite also has a liquid fuel engine, which enables it to attain its final orbit after breaking away from the rocket. This also enables necessary orbital or altitudinal changes. Once these various subsystems have been assembled or integrated, the exterior of the satellite is ensconced in layers of insulating and reflective covering. The electronic instruments aboard a satellite perform optimally at temperatures between 0 and 50 degrees Celsius. Satellites are subjected to considerable changes of temperature, from 160 to minus 140 degrees Celsius. The outer protective layers help maintain the satellite's components within an acceptable temperature margin. It is precisely because of the extreme fragility of these outer layers that satellites are assembled in white rooms. In a white room, dust is kept to a minimum by air filtration and the use of special clothing. Although highly complex, the components of the service module all have but one purpose: to ensure the smooth running of the other part of the satellite, its payload. The payload consists of the instruments that give the satellite its mission. High-resolution cameras, for example, in the case of an Earth observation satellite, or antennas and data processing systems in the case of a telecommunications satellite. All the steps involved in developing a satellite, its design, construction, integration, and testing, require about 3 years of painstaking work. Sending satellites into space, regardless of how sophisticated they are, does not fulfill the expectations of all scientists. Of course, some French astronauts have taken part in Russian or American missions. But Europe has never sent its own manned space vehicle into space. After weighing the pros and cons, Europe has finally opted for manned spaceflight. Thus was born the Hermes space project. The Hermes space vehicle will shuttle between Earth and the large Russian and American space stations. By the end of the 1990s, the European nations will, for the first time, have their own spacecraft to carry out manned space missions, the Hermes space vehicle. Hundreds Hundreds of engineers already have this new spacecraft on their drawing boards and have been confronting the technical challenges it poses. Overall, Hermes is similar to the American shuttle. However, the European spacecraft will be twice as small as its American cousin. It will be fitted with a piloting cabin located in the plane's cockpit, next to a pressurized cargo bay. The cargo bay will be divided into two parts, one for cargo and the other for the crew's living quarters and scientific activities. An additional module could also carry supplementary cargo and serve as a cargo bay access hatch for spacewalks. Hermes will thus be able to carry 3 people and 3 tons of equipment for an 11-day stay in orbit. By comparison, the American space shuttle can carry 7 passengers and up to 30 tons of freight for periods of 8 days. The propelling system that will put Hermes into orbit will also be different from the American shuttles. The U.S. space shuttle is attached on the back of a huge tank and lifts off by the thrust of its own engines. Whereas the Hermes space vehicle will have no engine. It will be attached to the end of a rocket that will launch it into space, exactly as if it were a satellite. This rocket, the Ariane 5 giant launcher, will be much more powerful than its predecessor, the Ariane 4 satellite launcher. Hermes' mass will reach 23 tons, much heavier than a regular satellite. Ariane 5 was primarily designed to ensure its occupants maximum safety. To make the launcher as foolproof as possible, its plans were considerably simplified. Ariane 4 consisted of 3 stages with 6 engines and had up to 4 boosters. Ariane 5, on the other hand, has only 1 stage with 1 engine and 2 side boosters. The extremely powerful engine will deliver a thrust of up to 110 tons and consume 15 tons of liquid fuel per minute. According to simulations, this simple design should make Ariane 5 10 times safer than Ariane 4. To further improve the safety coefficient, the European engineers designed other devices, such as a propeller ejection system with parachutes to brake the descent. The seats will be able to get the astronauts up to 500 meters away from the spacecraft in only 2 seconds. One of the greatest challenges the Hermes designers face is its re-entry into the atmosphere. Because of its small wings, the angle of re-entry is more pronounced than the U.S. shuttles. As a result, overheating caused by the friction of air molecules against the external structures of the plane will be even more intense. According to computer models, temperatures could reach 1,700 degrees Celsius on the most exposed areas, such as the plane's nose, the wing's leading edges, and the lateral rudders. The spacecraft's belly and underside of the wings will be exposed to temperatures ranging anywhere between 1,100 to 1,400 degrees Celsius. To protect the occupants against the intense heat and to make Hermes as light as possible, the engineers will be using extremely resistant materials called composite materials. A composite material is made up of a network of fibers called reinforcement. The fibers are interwoven according to a very complex 3-dimensional design. This framework is then impregnated with a substance called matrix that can be a resin or a ceramic. The matrix fills the gaps between the fibers perfectly. This close union of the matrix and the reinforcement produces a highly resistant material. Composites can be covered with a finishing coat. Should tiny cracks form, the covering will self-repair. Once all these challenges have been met, Hermes will be able to carry out its first missions. It will shuttle to the Columbus Space Station, also of European design. It will dock at the U.S. Freedom and USSR Mir space stations. Pushing the frontiers of international cooperation, Hermes will open exciting new possibilities for the commercial and scientific development of space. The Hermes space vehicle already has a promising future in communications. Don't forget that when the gods were still frequenting Olympus, Hermes was the messenger of the gods and the great patron of voyages.